Hey everyone, welcome to another deep dive. Today we're going to be looking at force and motion.
Oh, yeah, some really
Some pretty fundamental stuff.
fundamental stuff.
Yeah,
Yeah.
I mean it's like literally what makes the world go round.
Yeah, definitely.
Um so we're going to try to unravel the mysteries of why things move, why they stop, what keeps them going.
Right.
We'll be debunking some common misconceptions along the way.
Okay.
And we're going to do our best to make this stuff really clear and understandable for everyone. So get ready for some aha moments. You might be surprised at how much force and motion actually impacts your daily life.
Yeah, you're right. These concepts are often taken for granted, but they really are constantly at work shaping our experiences from the way we walk to how cars operate and even the flight of a rocket.
Okay, cool. So when I think about force, I kind of immediately think of pushing or pulling something.
Yeah.
Is that a good place to start?
Absolutely. That's the intuitive understanding of force, and it's a great place to start. Basically, a force is any interaction that can change the motion of an object.
Okay.
It can cause an object to start moving, stop moving, speed up, slow down, or even change direction.
So if I'm pushing a shopping cart at the grocery store, I'm applying a force to it.
Exactly.
Yeah.
And the harder you push, the greater the force you apply and the faster the cart will accelerate.
Okay, that makes sense.
Okay.
Now, I've heard the terms balanced forces and unbalanced forces.
Okay.
Can you explain the difference?
Certainly. Think about a tug of war with equal strength on both sides.
Okay.
The rope stays put because the forces are balanced, they're equal in magnitude, but opposite in direction so they cancel each other out. This means there's no overall change in motion.
Okay.
An object at rest stays at rest. An object in motion continues at a constant speed and direction. That's the essence of balanced forces.
Okay, I'm picturing that tug-of-war standoff. So if one side suddenly gains an advantage and pulls harder,
Right.
that's where unbalanced forces come in.
Right. Precisely now the forces are no longer equal. And the rope will move in the direction of the stronger force. Unbalanced forces are what cause a change in motion, whether it's starting to move, speeding up, slowing down, or changing direction.
So in our shopping cart example, if I start pushing harder, that's an unbalanced force leading to acceleration.
You got it. And on the flip side,
Yeah.
if you apply the brakes in your car, that's also an unbalanced force causing the car to decelerate.
So balanced forces maintain the status quo, while unbalanced forces are the agents of change.
Exactly.
Now, what about this concept of friction?
Okay.
How does that fit into the picture?
Friction is a force that opposes motion. It's like a constant resistance that objects encounter when moving against a surface or through a medium like air or water.
Okay, so it's kind of like an invisible force trying to slow things down.
That's a great way to put it. Imagine pushing a heavy box across a carpeted floor. You can feel the resistance, right? That's friction at work.
Yeah.
The rougher the surface is, the greater the friction. That's why it's easier to slide a book across a smooth tabletop than a rug.
So friction is essentially a force that acts in the opposite direction of motion. Does that mean it's always working against us?
Not necessarily. Friction can be both a friend and a foe.
Okay.
While it can make it harder to move things, it's also what allows us to walk, drive, and write. Without friction, we'd be slipping and sliding all over the place. Think about trying to walk on an icy surface. It's tricky because there's less friction.
You're right. I never realized how much we rely on friction for everyday activities. So to summarize, we have forces which can be balanced or unbalanced,
Yeah.
and we have friction, which is a force that opposes motion.
Right.
Are we missing anything else in this foundational understanding of force and motion?
One crucial concept we haven't touched on yet is inertia.
Ah, yes. Inertia. I remember learning about it in school, but it always felt a bit mysterious. But is it related to those objects at rest stay at rest and objects in motion stay in motion ideas?
You're on the right track. Inertia is basically the tendency of an object to resist changes in its state of motion. It wants to keep doing what it's already doing, whether that's staying still or moving at a constant speed in a straight line. It's like a built-in stubbornness in the physical world.
So an object at rest wants to stay at rest, and an object in motion wants to stay in motion. It's all about resisting change.
Exactly. And this resistance to change is directly related to an object's mass. The more massive an object is, the greater its inertia, meaning it takes more force to change its motion.
Okay, that's starting to click. So a bowling ball has more inertia than a tennis ball because it's more massive.
Precisely. That's why it takes more effort to get a bowling ball moving. and to stop it once it's rolling.
I'm starting to see inertia everywhere now. What about that classic tablecloth trick where you yank it out from under a set of dishes?
Yeah.
Is that inertia in action?
That's a perfect example. The dishes have inertia. They want to stay at rest. If you pull the tablecloth quickly enough, the force isn't applied long enough to overcome their inertia, and they stay put.
Mind blown. So inertia is like this hidden force that's always trying to keep things in their current state of motion.
You could say that. It's not a separate force in itself, but rather a property of matter that governs how objects respond to forces.
Okay, let me see if I can summarize this. We've got forces, which can be balanced or unbalanced, and they interact with objects that have inertia, which is their resistance to change in motion. And then we have friction, which is a force that always opposes motion. Am I getting this right?
You nailed it. That's a great summary of the core concepts we've covered so far.
Wow. I'm feeling much more confident about my understanding of force and motion already. Before we move on, do you have any questions for me to test my knowledge?
I do. Imagine you're riding a bike and you suddenly hit the brakes. What happens to you and why? Think about which concepts we just discussed are at play in that scenario.
Okay, let me think this through. So I'm riding my bike, cruising along, and then I slam on the brakes. Well, my bike is definitely going to stop. But what about me? I'm going to keep moving forward, right?
You're absolutely right. That's inertia in action. Your body wants to continue moving at the same speed and in the same direction it was going, even though the bike is stopping.
So I'm going to lurch forward over the handlebars. I've definitely experienced that before, and it's not a fun feeling.
Exactly. And that's why wearing a helmet is so important when riding a bike. It helps protect your head from that sudden forward motion in case of a sudden stop.
Okay, that makes perfect sense. Inertia is a powerful concept. So we've covered forces, balanced and unbalanced, friction and inertia. What's next in our exploration of motion?
Well, we've talked about how forces can start or stop motion, but what about how they change motion? That's where Newton's laws of motion come in. They provide a mathematical framework for understanding how forces influence the motion of objects.
Newton's laws. I remember hearing about those in school, but to be honest, they always sounded a bit intimidating. Can we break them down in a way that's easy to understand?
Absolutely. Newton's laws are actually quite intuitive when you connect them to everyday experiences. Let's start with Newton's first law of motion, which we've already touched upon when discussing inertia.
Okay, I'm ready. So remind me, what's Newton's first law all about?
Newton's first law of motion states that an object at rest stays at rest, and an object in motion stays in motion at a constant speed and in a straight line, unless acted upon by an unbalanced force.
So it's basically the law of inertia, right? Things want to keep doing what they're already doing unless a force makes them change.
Exactly. Inertia and Newton's first law are two sides of the same coin. It's this inherent tendency of matter to resist changes in motion that makes this law so fundamental.
Okay, I'm feeling good about Newton's first law. What about the second law? I think I remember something about force, mass, and acceleration being involved.
You're right. Newton's second law of motion explains how the force acting on an object is related to its mass and acceleration. The equation is famously simple, F equals ma. Force equals mass times acceleration.
Okay, let's break down that equation. So if I apply a force to an object, it will accelerate.
Precisely. The acceleration of an object is directly proportional to the net force acting on it. This means that if you double the force, you double the acceleration.
That makes intuitive sense. The harder you push something, the faster it speeds up. What about the mass part of the equation?
The mass of an object is a measure of its inertia, its resistance to change in motion. The greater the mass of an object, the smaller its acceleration will be for a given force.
So a heavier object will accelerate less than a lighter object if the same force is applied.
Exactly. Think about pushing a shopping cart versus pushing a car. With the same amount of force, the shopping cart will accelerate much faster because it has less mass.
Okay, starting to see how this all fits together. Force causes acceleration, and the amount of acceleration depends on both the force applied and the mass of the object. So if I want to accelerate an object quickly, I need to apply a large force or have a small mass.
You've got it. And that's why race cars are designed to be lightweight and have powerful engines. It's all about maximizing acceleration.
This is fascinating. I'm starting to see how these seemingly simple laws have profound implications for everything from sports to engineering. Now we've covered Newton's first and second laws. What about the third law? What does that one tell us?
Newton's third law of motion states that for every action, there is an equal and opposite reaction. This means that whenever one object exerts a force on a second object, the second object exerts an equal force back on the first object. but in the opposite direction.
Yeah, so if I push against a wall, the ball is actually pushing back on me with the same force.
That's exactly right. It may feel counterintuitive, but those forces are always present, acting in pairs.
Okay, my mind is slightly blown right now. If the forces are equal and opposite, why don't they just cancel each other out?
That's a great question, and it's where many people get confused. The key is that the forces are acting on different objects. You exert a force on the wall, and the wall exerts an equal and opposite force back on you.
I see. So the forces don't cancel each other out because they're affecting different things.
Precisely. Think about jumping. You push down on the ground, the action, and the ground pushes back up on you with an equal force, the reaction. This upward force from the ground is what propels you into the air.
Wow. I never thought about jumping in terms of Newton's third law, but it makes perfect sense.
Yeah. It's a great illustration of how this law works. Another example is a rocket launch. The rocket's engines push hot gas downward, and the gas in turn pushes the rocket upward with an equal force, propelling it into space.
That's incredible. So Newton's third law is all about these action-reaction pairs of forces that are always equal in magnitude but opposite in direction and act on different objects.
You've got it. It's a fundamental principle that governs all interactions between objects in the universe.
This is heavy stuff. I need a moment to process all of this. Do you have any questions for me to ensure I'm grasping these concepts?
I do. Imagine you're in a car that's moving at a constant speed, and you toss a ball straight up in the air. Where does the ball land? And can you explain why using the concepts we've discussed?
Okay, let's visualize this. I'm in a car moving at a constant speed, and I toss a ball straight up in the air. I'm tempted to say it lands behind me, because the car is moving forward.
Yeah.
And the ball is kind of suspended in the air for a moment.
That's a common misconception, and it's a testament to how our intuition can sometimes clash with the laws of physics. The ball actually lands back in your hand.
Wait, really? But why? Wouldn't the car move forward while the ball is in the air?
Remember, the ball is already moving forward at the same speed as the car when you toss it. It's got that forward inertia.
Right.
So even though it's moving upward, it's also continuing to move forward at the same speed as the car.
Ah, so it's like the ball is carrying the car's forward motion with it,
Yeah.
even as it goes up and down.
Exactly. It's all about relative motion. From your perspective inside the car, the ball only appears to move vertically. But from an outside observer's perspective, the ball is following a curved path, moving both upward and forward.
That's incredible.
Yeah.
So it's like the ball is secretly tracing a diagonal path through the air, but I only see the up and down part because I'm moving along with it inside the car.
You got it. This example beautifully illustrates how inertia and relative motion can create seemingly counterintuitive results.
This deep dive has been a real eye-opener. I feel like I've gained a whole new understanding of how forces and motion shape our everyday experiences.
It's been a pleasure exploring these concepts with you. And remember, this is just the tip of the iceberg when it comes to the fascinating world of physics.
I'm definitely eager to learn more. But for now, let's recap the key takeaways from our deep dive into force and motion.
Okay.
We started with the basic concept of force, which is any interaction that can change an object's motion. We learned that forces can be balanced, resulting in no change in motion or unbalanced, causing acceleration.
We then delved into friction, which is a force that always opposes motion, acting like a constant resistance. And we can't forget inertia, that stubborn property of matter that makes objects resist changes in their motion. The more massive an object is, the greater its inertia.
And then we explored Newton's 3 laws of motion, which provide a mathematical framework for understanding how forces govern the movement of objects. Newton's first law is essentially the law of inertia. Newton's second law relates force, mass, and acceleration through the famous equation F, its filler. And Newton's third law describes the always present action-reaction pairs of forces that act on different objects.
We've seen how these laws, along with the concepts of friction and inertia, are at play in countless everyday scenarios, from riding a bike to launching a rocket.
This deep dive has definitely given me a newfound appreciation for the hidden forces that shape our world. To all our listeners out there, keep those minds curious, and we'll catch you on our next deep dive into a new and fascinating topic.